So in this video, we're going to continue on with the idea of the sampling distribution and see how we know if we can use the properties of the normal distribution that we've seen so far in chapters 3 and 6. A very important theorem for us in this class is the central limit theorem. And if we can meet these conditions, then we can say the normality criteria are met, or that our sampling distribution should be approximately normal, and we can apply some of those properties we've seen. The first condition, and the condition that we want to check, is that the sample is randomly selected from the population. The sample that we have is randomly selected. As well, the observations should be independent of each other. They're not affecting one another. Just like we saw back in chapter 5, that's something that you don't have to check for. We're going to assume this in our course. As well, the sample can be taken with or without replacement. Just like with a deck of cards, you could either put the cards back in or you could leave the cards out of the draw. But what we want to focus on is the sample, and is it random? Condition number 2, the sample size, which is n, is large enough so the sample expects at least 10 successes and 10 failures. So in this chapter and the next, our question will pretty much have two answers. Would you vote for this candidate either yes or no? Do you prefer Coke or Pepsi? One of them will be a success and the other will be a failure. You need at least 10 people or 10 objects on each side. We can calculate this mathematically with a couple of formulas. N times P, where N is your sample size and P is the population proportion, that will give you your success number. And N times 1 minus P will give you your failure number. They need to be at least 10 or more. That's another thing I'm going to ask you to check. When I ask you to check the central limit theorem or to check the normality criteria, I want you to make sure that it's a random sample and then you have at least 10 successes and 10 failures. And note how many successes and how many failures you have. The third condition is noted in our text. It says if the sample is collected without replacement, then the population size must be at least 10 times larger than the sample size. We're not going to focus in on this one for a couple of reasons. Reason number 1, a lot of times we don't know if the sample is done with or without replacement. That information is not given to us. As well, we won't always know the exact population size, so it may be difficult to judge is the population size at least 10 times larger. We are also going to assume this is true for the most part. We're going to check and make sure we have a random sample and we have at least 10 successes and 10 failures. Let me show you a couple of situations where we can apply the central limit theorem. Example 1 is a scenario we've seen before. So suppose a college has a total of exactly 10,000 students, that's our population, and 25% of students live less than 5 miles from campus. So that is our P, it's 0.25, that's from the population. We are planning a random sample of 100 people without replacement. I want to know, are the criteria for the central limit theorem met? So first thing you need to check is, do we have a random sample? I can say that is met. So right here it says we're planning a random sample of 100 people. The next thing you need to look into is your success number. That's N times P, where N is your sample size, that's 100, times P, which was noted to be 0.25. This gives us 25. Since it's over 10, we can say that is met. For my failure number, that's N times 1 minus P. So that would be 100 parentheses 1 minus 0.25. And you could type this in your calculator all at one time, just like we did with the standard error formula in a previous video. This is going to give me 75 when you type this in. It's met because it's over 10. And I didn't type this into the calculator but because I know a little shortcut. I know that my success number and my failure number always add to be the sample size. So since my sample size was 100, since this was 25, this had to be 75 because 25 plus 75 is 100. So I could answer the question, are the criteria for the central limit theorem met? I could say yes. And what that means is that our sampling distribution should be approximately normal. I'm not going to see a skewed left curve or a skewed right curve. It should be pretty much bell-shaped. And I expect P of 0.25 to be in the middle. And I could calculate the standard error and go up a couple of those and down a couple of those. And we'll do that in the next video. But let's look at another central limit theorem example to wrap up this video. It says, according to the Regional Bar Association, approximately 66% of the people who take the bar exam to practice law in the region pass the exam. A random sample of 200 people who take the bar exam is going to be taken. Check the normality criteria. That's another way to say check the central limit theorem. So we just go through and we note that these characteristics are met. Number one is that a random sample, not a convenient sample, not a voluntary response sample. Say that's met because of the wording right here. My success number. How many people do I expect to pass the bar exam? That's N times P. This time my sample size is 200. Times P in this case is 0.66 from the 66% who pass the exam. This will give me 132, and because that's over 10, I can say it's met. For my failure number, N times 1 minus P is 200 times 1 minus 0.66. And this is going to be 68. You could take 200, subtract 132, and that will give you 68. I know these two have to add to be the sample size of 200. Or you could type this into your calculator. Either way, you'll get 68. They're both over 10, so this is met. That means I could apply what I've seen from the empirical rule and means and standard deviations with this normal curve. This sampling distribution is approximately normal, so 0.66 would be in the middle, and we'll calculate the standard error in the next video as well.